Welcome back. In this video we're going to talk about spheres and cylinders in R3. To begin this conversation, let's recall our discussion of circles in R2. To this end, we define a circle as having a radius and a center. Maybe we call our circle capital C in R2, and this is subset notation. We're going to think about a circle as a collection of points. So the way that we read this notation is C is a subset of R2. And again, we write it as like a long C with a little line. It means everything contained in C is in R2. And we're thinking about a circle as a collection of points has a radius R, which is a positive real number. The radius we think of as a positive real number. And a center point, which we think of as an ordered pair h comma k. This is a point in R2. It's a point in R2 where h is the x coordinate of the center, or the first coordinate of center of circle, and k is the second coordinate of the center of circle. With this in mind, we think about the circle as the set of all points in R2 that are r units away from the center. Let's go ahead and write this. So when we think about the circle, a circle in R2 is a collection of points in R2 that have a distance of r units from the center. And we can actually use our distance measurement, aka the 2 norm, to introduce notation to discuss this. In other words, we think about the circle as being the set of all points x comma y such that the distance between x comma y and h comma k is equal to r. All right. We know a distance formula that we can use to calculate the distance between points. In particular, we know that the distance between xy and hk is given by the difference between the first coordinates squared plus the difference between the second coordinates squared. Take the square root, and then we set this equal to a constant r. And we can do a further simplification to say that the circle is the set of all x comma y such that x minus h squared plus y minus k squared equals r squared. And this is writing the distance formula without the square root. Okay, and I'm going to do one more simplification. This is not so important for today's work on spheres, but it becomes really important when we start talking about ellipsoids. A ellipsoid is to a sphere what a box is to a cube. It's a generalization of the perfect scenario. And one of the things you can do here is if you divide both sides by r squared, you start to get intuition for later. So notice there are a few different ways we can think about a circle. A circle is all points in R2 that are equidistant from the center, which we can write in one of these three equivalent ways. Okay. You may have seen in the past that in calculus, we did not think about these as sets. We literally just gave the equations for the x and y. And notice this is an implicit relation. And this we'll get into. In your previous calculus class, this is the one we focused on. Or maybe if you brought the r squared over to the other side, you got this. And we're going to go ahead and skip over to Mathematica right now just to show how to graph this thing. And then we're going to use our intuition on this implicit relation to define a circle in order to come up with an equation for a sphere. Remember, implicit relations in mathematics correspond to what we call a contour plot command in Mathematica. And in particular, this is going to be in 2D, so our contour plot will also be in 2D. Let's switch over to Mathematica and plot this thing out. Here we are in Mathematica, and we'd like to plot a circle with variable center and defined radius. To do this, I'm going to go ahead and define three variables. Perhaps I'll call my h coordinate for the center 2, my k coordinate or my y coordinate, second coordinate, I don't know, let's be a little bit exotic and go negative. And then maybe we call our radius 4. We're going to go ahead and graph this implicit relation using contour plot. Mathematica is making a suggestion here. I'll go ahead and type it all out. So I'll get to the end. I'm going to go ahead and end comment this. This is just kind of good code so I know where the end is. I'm going to plot x minus h, and I'd like to square. So on my Mac I put control caret square. Let's pretend that you don't know the control or it's different on your Windows. I'm not really sure what it is on Windows. I can go to Basic Math Palette. I can go over to the button that has the square. So I go ahead and highlight this, and then I square it. And this is going to be y minus k. And then I'm going to set this equal to r squared. Remember that in contour plot we use the double equals because it's actually a logical equals, meaning to say Mathematica is going to test for truth. I'm going to let x run from It looks like I should at least have up to 6 because 2 plus 4 is 6. So maybe I go to from -8 on the lower side to 8 on the upper side. And then y goes from, what do we say? -3 is going to be -7. So maybe the same thing, -8 to 8. Okay, let's go ahead and evaluate this thing. You see how I don't see the axis? Let's go ahead and see if we can do axis origin, and let's go 0, 0. Let's evaluate again. I think axis origin, I'm not sure what's going on here. Yeah, but you see the center there, right? We could actually graph the center if we wanted to. So we could actually go show. Let's go ahead and turn this into a double graphic. So remember, show allows me to combine different graphics. So in this case, I'm going to define a graphics, not a graphics 3D, because it's not graphics 3D. And I'm going to actually graph a point. And the point I'm going to graph is h comma k. So here we go. There's the center. And notice that the radius of this sucker is 4 by construction. And what's really cool about this is I could zoom out a little bit just to make this a little easier to see. I can change now. Maybe we wanted to go up to, I don't know, 4. It's going to be right on the brink there, right? And I could also go to negative in my y coordinate. So let's go negative, excuse me, my x coordinate. And then I could change, I could make the radius smaller. Right? So that allows me to kind of play with this. One open question that I have to answer is, how do I get the origin through? I could hack it quite quickly by just drawing a line through the origin. I don't know if we want to do that. Maybe we can go ahead and do that, right? So here, I could do a graphics. So let's do a line, and this line is going to be through 2 points. It's going to be through the point, let's go -8 comma 0 to 8 comma 0. What is it complaining about? It's complaining about the fact that I haven't marked the line as such. There it is. So what I just drew is a line through the origin, right? And then I could draw another line through the other origin. So instead of the x coordinates being changed, I'll change the y coordinates and keep the x coordinates as 0. Delete this. Okay, so that just gives me an axis. It's not the most beautiful solution to this problem, but it does tell me where the origin is. And we can go ahead and check that if I put the origin there, if I put this at the origin, that I get a circle of radius 2. Okay, let's return to our paper and pencil analysis. Now that we think about the circle as all points that are r units away from the center, could you guess how we define a sphere in R3? Just like we said that a circle was the set of all points with 2 coordinates, x comma y, such that the distance between each point and the center was a constant radius, so too we can use this intuition to define spheres. The way we thought about this set, I guess we should be really explicit. This is the C, capital C, and you can see that it's capital because I put little serifs on it, equals the set of all, this is set notation, ordered pairs, or points, x comma y, such that the distance from xy to center hk is equal to r. This gives us the exact template to allow us to define spheres in R3. In other words, we can generalize circles in R2 to spheres in R3. We define a sphere as the set of all points in R3, of course. This is the major idea. So instead of x comma y, we would have x comma y comma z. And we would say that these points are r units away from the center of our sphere. And maybe we call our center h comma k, and I'm going to do script L. It's important to write it as a script so that it doesn't look like the number 1. Let's go ahead and look at how we would define this. So a sphere, we'll call it capital S, is going to be a set of points in R3. We need ordered triplets in this case. And we've already defined the distance formula in R3 as taking the square root of the sum of the squares. In this case, this would be x minus h squared plus y minus k squared plus z minus l squared. And then the claim is that the sphere has the property that this distance, the distance between any point on the sphere and the center, is a constant r. And of course, we say that r should be a positive real number. Just because we expect to measure distances as positive. Of course, we could clear the square root, and this would give us an equivalent mechanism for defining a sphere, which would bring the square root into a square on the other side, since squares are the inverses of square roots. Minus L squared equals R squared. And then we could have the same algebraic trick that we did last time when talked about circles, which is to bring the R into the denominator on each factor. This algebraic technique is really relevant when we start talking about ellipsoids. One of the things that we will see is we could have different denominators on the x, y, and z factors, and those denominators would be called the length of the semi-axis. This gets into deep mathematics of quadratic forms and gets into stuff in linear algebra, which is one of my favorite things in life. So any of these define a sphere, and the thing that I want to say is spheres are collections of points in R3. Previously in your life, we defined surfaces not by looking at sets, but just by looking at the relevant formulas that define the sets. And we can do that again here. If we look at this formula, which writes x, y, and z implicitly in terms of each other, this is not an explicit relationship, but instead an implicit relationship. We saw that in order to graph implicitly defined graphs, we used contour plot. This is going to be in 3D, so we'll use the contour plot 3D command. Let's go ahead and create a graph of a sphere with center h, KL, and radius R in Mathematica. We want to define a sphere and visualize this using Mathematica. Let's go ahead and define the center points of the sphere. Of course, we have h, which is the first coordinate. We'll call that equal to perhaps 2. K, we'll do something exotic. Oh my god, a negative. And then L, perhaps we want to do a script L. Well, I guess we could just call it L for now, and then go to 2. Maybe we'll do 1 to do something different. Let's call the radius of the sphere 5 for now. As we noticed last time, this is going to be a implicit relation, which means we're going to use contour plot 3D. And we'll go ahead and comment. This is the commenting contour plot 3D command. Okay. We do the same thing that we did last time, which is x minus h. We're going to go ahead and square it, which we did using the keyboard shortcut for squaring. Y minus k, again we do the keyboard shortcut for square. And then let's do z minus l. We're going to go ahead and close these with parentheses. And let's go ahead and use the math palette just to make this super explicit on what it is that we're doing here. So we go and push the square, and then we set equal to r squared. So it's the set of all x, y, z, since this is equidistant. I need to tell Mathematica the values of x, y, and z that I want to hold. Here, I'm going to have a radius 5. My y coordinate starts, or x coordinate starts at 2, so it's going to go from 2 plus or minus 5. Maybe I'll go to 10 just to make it large enough. Same thing in y, I'll go from negative 10 to 10. And in z, I'll go from negative 10 to 10. Let's go ahead and evaluate. So with max, I hold shift and hit enter, and that's how I evaluate this thing. I tend not to like the mesh on this, so I'm going to go ahead and say, please Mathematica turn mesh off. So now it's a sphere. And I also like to control the contour style. So I can do contour style. Directive allows me to combine many different styles together. Personally, I like blue, and I'm going to turn the opacity to something like 20% to allow me to see through it. Okay, so now there's that sphere that I wanted. I'm going to go ahead and combine this with a graphics 3D by using the show command. I better indicate that this is the end of show. Here's the end show command. And my graphics 3D is going to be a point. So here's graphics 3D. It's a 3D graphics, that's what I wanted. And it's going to be a point. And the point is going to be H, comma, K, comma, L. So now that's the center of that. And perhaps I want to make the point size a little bigger. So here I use open and close curly brackets. And the point size is always kind of confusing. Perhaps we go up to 2. See how big that one is. Oh, it's complaining because oh yeah, and then this has to be capital. Yeah, that's a little bit too big, so let's go down to 1. Alright, there is the center, and then we can put the axis. This one will definitely work. Axes origin, and then we'll tell that we want the axes, all 3 axes, to go through the 0 point. And you see there's the x, y, and z, and I can actually change. Let's go ahead and test if we were to set all these equal to 0, that indeed we would get the sphere through 0. Okay, there it is. And then maybe we want to turn the radius from 5 to 2, so it should get a lot smaller. And then maybe we want to move the radius 5 units in the negative direction along the x-axis. And perhaps we want to use 5 units or 4 units in the y direction. Now it's in the XY plane. The center of that thing is in the XY plane. And then we want to move it down 1. Right? That's how we visualize. To do this, I just click my mouse and kind of scroll it around. That's how I get that visual. And then perhaps if you wanted to turn the mesh back on, you could put true. Kind of hard to see. And of course I could just make this larger by... So there's the sphere. In the next video, we'll talk about cylinders and we'll look at an example of spheres. See you there.